Hello, welcome to this lesson of our journey through writing mathematical proofs, and this is the video that talks about proving mathematical statement using contradiction. Okay, so let's get straight into the video. Now, there's a proposition here that I want to prove, and within these set of problems I'm going to prove, I'm going to use contradiction. There's one particular problem that I might not prove with contradiction because it's a claim that I'm going to prove, and I'll use that to prove another problem. Okay, so yeah, for every real number x that is in this interval, sine of that number plus cosine of that number is greater than or equal to 1, and we're going to prove this using contradiction. Okay, so the proof is that we suppose that a sine of x, you have to suppose a negation of this statement, sine of x plus cosine of x is less than 1. The negation of this whole statement is going to be sine of x plus cosine of x is less than 1, right? Because the actual statement is greater than or equal to 1, so if you negate it, then it's less than 1. Now, if you suppose that, but we're going to try to prove something, okay, that this shouldn't be the case. If you're able to show that this shouldn't be the case, then it's a contradiction. Okay, so suppose that there's a negation of it, right? We also know that for all x in this interval that we're talking about, what can you say about sine of any number from 0 to pi over 2? The sine curve looks like this: 0 to pi over 2. This is the sine curve, right? It comes here all the way to this place. So here is 1, and you could see that per the graph, you can say that this sine of x is greater than or equal to 0. It's never less than 0, right? And also, you can say that same thing for the cosine of x, right? Cosine of x is also greater than or equal to 0 for every x in this. Same, you can use the cosine function or the graph of it to check it out, right? Then this means that sine of x plus cosine of x will always be, we are saying this is less than 1, but we know that this guy is greater than 0. We know also that this guy is also greater than 0. Then if I try to square both sides of this equation or this claim, all right, that I said, this part, if I square both sides, it means I'm going to have sine of x plus cosine of x squared, right, is less than 1 squared. This is going to give me sine squared of x plus cosine squared of x plus 2 sine of s cosine of x is less than 1, right? But we know that this guy, sine squared of x plus cosine squared of x, is given us by 1, and this from a trigonometric identity. So you're going to get this statement here, less than 1. So if I send this 1 to the other side of the inequality, I'm going to have 2 sine of x cosine of x should be less than 0, because I'm going to have 1 going to this side, and that gives us 0 there. Now what this tells us is that this is going to give us, dividing through by 2, I'm going to have sine of x, right, cosine of x less than 0. Now this whole statement that is telling us is that for every x, for this claim that we made, we've been able to deduce that for every x that we pick in this interval 0 to 2, 0 to pi over 2, the product of the sine of that function, that value, and then cosine of that value is less than 0. That's what we've been able to prove. But we also know that sine of x is always greater than or equal to 0 for x being in this interval, and cosine of x is that. So if you multiply these two, they are both non-negative, right? So if I multiply two non-negative values, I should get something that is non-negative, right? This means cosine is not negative, sine is not negative, and it means their product will also not be negative. It just a normal multiplication rule from integer values, right? So if you have two non-negative integers and you multiply them, you get a non-negative integer, right? So this means this claim that we've gotten here is a contradiction, because we know it's a contradiction of the fact that let me write here, of saying that sine of x is greater than or equal to 0 and cosine of x is greater than or equal to 0, right? So if you have two values that are greater than or equal to 0 and you multiply them, you get something that is also greater than or equal to 0. It means this is a contradiction. So, and this result is coming from this claim. So hence this claim is false, and that we must have sine of x plus cosine of x greater than or equal to 1 rather. So then that ends the proof. So after writing this whole thing, contradiction, that you can end everything with this statement, right? So that is how you prove by contradiction with this. Let me go to some claim I'm going to prove. This is not contradiction, but I'm going to use this to prove that square root of 3 is actually an irrational number, right? So let a, b, p be integers with p prime. Prove that if p divides a, b, then either p divide a or p divide b. So that is a very good claim that you're going to use. And here I'm going to use something called Zorn's lemma. And if you've not heard of that, I will just state it and we'll use it, okay? So our proof is that we know p divides ab, right? So this means that ab can be written as a scalar multiple or an integer multiple of p, right? So kp, where k is also integer. All right, so k is an integer. If you've been following my proofs, you realize I normally use the divisibility properties, right? So if we have that p divides the product of a and b, right? So this ab means the product of that. So if p divides a, then we are done, right? Then we are done. If p divides a, then indeed, what we are trying to show is that if p divides ab, then either p divides one of them. So if the numbers that are given to us are being given in such a way that p divides a, then automatically you are done with the proof, right? Now suppose that p does not divide a, then it's our proof, or it's our responsibility to prove that. So we have to prove this p divides b, right? So we are supposed to prove that if p does not divide a, then necessarily we have to get that p divide b, right? That's what we're going to do now. So we know p divides ab, right? And ab is equal to kp, and we are assuming that p does not divide a, right? And since p does not divide a, implies that what? The GCD of p and a is equal to 1, because p is prime. So if p does not divide a, that is, a is not any integer multiple of p, then p cannot go into a. So it means the only common factor that can divide both a and b, p and a, is 1, right? That is the GCD, greatest common divisor. Now by Zorn's lemma, this is lemma, right? It states that the GCD of two integers, it can be written as the linear combination of the two numbers, right? So it means the GCD, which is 1 of p and a, can be written as a linear combination, something like 1 is equal to ma plus np. So let me call this a first equation, right? So what Zorn's lemma is saying is that if you have the GCD of two numbers, you can write it as a linear combination of the two numbers, right? So having this lemma, what we can say is now we can try to multiply b through the whole of equation 1 and have b being equal to mab plus npb, right? But we know that ma is also giving us, or maybe ab is giving us kp. So I can put it there. So I have mkp plus npb, right? So I'm going to have mk plus nb multiplying p is equal to b, right? I know b is appearing here, but that's not our interest. Now this can be written as b is equal to some ko multiplying p, where ko is equal to mk plus nb being an integer, right? So we've been able to, if p does not divide a, we've been able to write b as an integer multiple of p, right? So it means that what p divides b. So if p does not divide a, in this instance, if p does not divide a, we've been able to prove that surely p would necessarily divide b. So that's the whole proposition. This is true, and so that ends the proof. This is true for a prime number p dividing the product of two numbers. Right. So if a prime number divides the product of two numbers, then p would divide one of them. That is a claim, right? So that's the proof to it. Now let's go to prove that square root of 3 is irrational. Normally, most books prove that square root of 2 is irrational, and I chose to prove that square root of 3 is irrational. And before that, I needed that claim, right? So that's why I proved that claim that I used. So show that square root of 3 is irrational. Now we're going to prove this by contradiction. Now suppose by contradiction that square root of 3 is rational, right? So that is the negation of your original statement. Now, if you suppose that this guy is rational, then by the definition of rational numbers, I can write square root of 3 as some a over b, or maybe you can say, a over b, where the GCD of a and b is equal to 1. The reason I'm using GCD here is I'm not going to use this in any of my proof, but I have to state it. You can state with a statement that where a and b have no common factors except 1, but you can just write it as the GCD of a and b to be 1. That means the greatest common divisor, the only divisor for a and b is 1. If the greatest common divisor of a and b is 1, then it means that's the only divisor of a and b, meaning that in particular they don't share any common factor except 1, right? Now if I square both sides of this little equation I've written here, I'm going to have 3 equals a squared over b squared, and in this I'm going to have that a squared equals 3b squared, right? Now I've been able to write a squared as a multiple of 3, a scalar or an integer multiple of 3, because b, right, so of course you have to also say that b is not 0. That is the definition of rational numbers, right? So I've been able to write a squared as an integer multiple of 3, because if b is an integer, right, so where I can still go ahead and say that since square root of 3 is positive, I can say a and b are positive integers, or you can just say they are integers, right? So I know that a and b are integers, so if I square any of them, I get an integer back, right? So actually I can say 3 divides a squared. Now the idea is, this is because you can write a squared as some integer multiplying 3, and that is what is happening here. And this implies that 3 divides a multiplying a. And if you recall our claim here, that if you have a prime number that divides the product of two numbers, then the prime number divides one of them, right? And here we have the prime number to be 3 dividing the product of a and a. So this means that by our claim that we stated, 3 actually divides a, meaning a is equal to some 3 multiplying a constant or an integer k, right, where k is an integer. Now we go ahead and then try to find a squared. A squared then will be equal to 9k squared, right? Squaring this side, I get 9k squared, right? Now I have this, and it means that I'm supposed to go and use this and put a squared back inside that. If I put a squared inside that equation, I'm going to have something like 9k squared equals 3b squared, right? So it means I can say b squared is equal to 3k squared. Again, this implies that what? It implies that 3 divides b squared, because b squared can be written as 3 multiplying an integer. Alright, so I can say that, and then this means that again 3 divides b multiplying b. Using the same lemma we stated and proved, you can say 3 divides what? B, meaning that b is equal to 3 multiplying some integer, say l, right? And so we've gotten 3 dividing a and 3 dividing b. What does this tell us? It tells us that 3 can go into a and also go into b. But what we said here earlier was that the GCD of a and b is 1. That means the only number that can divide both two numbers is 1. But we've been able to show that if we suppose a square root of 3 is a rational number with this property, a rational number can be broken down into its simpler form, that is a over b, then this is not working, because like after stating that the GCD is 1, we've been able to show that actually there's another number 3 which also divide both a and b. So this is a contradiction. So this is a contradiction of the fact that GCD of a and b is equal to 1, right? So we must have square root of 3 to be irrational, right? And that ends the proof. So that's how you use contradiction to prove statement. Yeah, so that's the end of the video, and I'm gonna go ahead and still do other videos as well, so stay tuned to join my channel as I try do videos on writing mathematical proofs. If you have not subscribed to my channel, kindly subscribe, and see you in the next video. Thank you.